Hello everyone, my name is Jyotishwar Reddy. Today I am discussing about the funnel project of recurrent neural networks. Now I am going to explain about exploring time series analysis with neural networks. A journey through RNN and LSTMS for simple sine waves to complex retail data. Coming to the part one, here we have datasets time series dataset. I have selected retail sales dataset from Kaggle for my final project. Here is the dataset overview, the name of the dataset, data type, source, link to dataset, time series span. The dataset covers transactions over several years, providing a longitudinal view of customer purchase behavior. The dataset contains transaction ID, date, customer ID, gender, age, product category, quantity, price per unit, total amount. The dataset is made up of thousands of transaction records. Each of lists the purchases. The huge amount of data make it possible to detail time series research. I can use this dataset to look into how sales trends to change over time and age, gender, and product affects people buy things, and seasonal patterns and customer preferences can be found in the research, which is useful for making smart businesses. Here is some primary objectives of the dataset analysis: determine which product categories, optimize stock values, segment customers based on customized marketing strategies. Coming to the next part is part two is RNN, simple RNN with sine wave data. Here is the retail sales dataset, comprehensive data analysis goals. Comprehensive data includes transaction details, customers, demographics, and product information over several years. Coming to analysis goals, examine customer behavior, analyze sales trends, and project future sales. Here is the simple RNN with sine wave data. Coming to this, there is a data preparation, sine wave divided into 50 time step sequences. Next, second step is model composition. In model composition, there is simple RNN layer with 50 neurons followed by a dense layer, and the final one is results. Test loss of 0.5103, predictions closely matched actual value. Here is the diagram of neural networks: input layer, simple RNN, output layer. The diagram shows RNN model used for sine wave prediction. The first layer, input layer, takes the time series data as input. The middle layer, simple RNN layer, process patterns in the data. And last layer, output layer, predicts the next value in the sine wave. The report of sine wave data. In this part of the project, I explored the potential of a simple recurrent neural network RNN to predict future values of the sine wave using a dataset I created with 1000 data points. This report details how I prepared the data, structured the model, trained it, and accessed its performance. Coming to data preparation, in data preparation for this test, I made a sine wave that went from 0 to 100 times units, which is one full turn of the wave. The main objective was to shape the continuous wave into a form that could be used by an RNN. I split the wave into sequences, and each set of 50 values in a row suggests the next wave. Model structure. In the model structure, the neural network was constructed to the both effective and simple, as and it includes two important layers. One is simple RNN layer, another one is dense layer. The simple RNN layer employs the hyperbolic tangent and its activation function and consists of 50 neurons. It is designed to capture the temporal pattern of the sine wave. Dense layer, coming to a dense layer, which follows the RNN value, employs a single neuron to project the sine wave predicted. next wave to minimize the dispensary between the predicted and actual value. Next, training the model. The model was set up with the Adam optimizer and mean square error as the loss friction, which is standard for regression tasks such as ours. I conducted the training of 50 epochs with a batch size of 32, utilizing 80% of data for training and remaining 20% for the validation to prevent the model from memorizing the data. Evaluating the model. Upon completing of training, the model attended the test loss of 0.5103, significantly that the mean square deviation between the predicted and actual values was relatively minimal. The loss decreased throughout the initial epoch and stabilized. Here the outcome that shows this. The model prediction was closely aligned with the actual sine wave data points as illustrated in the plot comparisons. The evaluated accuracy in the prediction indicates that the RNN effectively generalized from the training data to the previously unobserved data in the test set. Coming to the part 3, in part 3, uh, RNN LSTM neural network. In this, we have understanding the gradient problems, vanishing gradient, exploding gradient. Vanishing gradient error signals dis- diminish as they propagate backward, hindering learning of long-term dependencies. Uh, In coming to exploding gradient, excessive growth of gradients during back propagation leads to poor learning and instability. In these two gradients, the vanishing gradient problem is challenge when training deep neural networks, particularly sequential models such as RNNs. During training, the model adjusts its weights via a technique known as back propagation. However, the model attempts the route to error signals back via multiple layers. The gradient which describe how much the weight should be modified become very small. This problem is especially prevalent when activation functions such as sigmoid or tan are utilized. Coming to exploding gradient problem, in this exploding gradient problem is an inverse of the vanishing gradient problem during back propagation. Gradients increases in size rather than decrease in magnitude. This occurs when the model's parameters or gradient multiplication during training are extremely large. When this happens, the weight is earlier levels are set to abnormally high values. Both the vanishing gradient problem and the exploding gradient problem show how hard it is to train deep learn neural networks. These things make it hard for models like simple RNN to learn from patterns that depends on each other in complicated or long-term ways. Coming to question 3.2, one of the first neural network model made to deal with sequential data was the simple RNN, which stands for the basic recurrent neural network. It gets information from one step in a chain to the next, which let it keep track the relationship over time. Simple RNN are easy to understand and useful for the some tasks, but they aren't great as solving complex sequential problems because of some issues with their design. Recurrent neural networks RNN. Here is the design. One big problem with simple RNNs is that they have trouble dealing with long-term relationships when working with patterns. You sometimes need to remember things that happened a long time ago. The exploding gradient problem is another problem with simple RNN. This happens in the exploding gradient problem in another problem. This happens. This make it changes itself randomly, which leads to poor performance. Gradient clipping and other methods can help, but they don't fully fix the problems that simple RNN has their core. Also, simple RNNs can't describe complex patterns in data very well. They use a single hidden state to hold all the knowledge about the sequences, which isn't always enough to show complex relationship. Finally, simple RNN are computationally inefficient with longer sequence. Training can be slow and resource insensitive because it's only process one step at a time, especially when dealing with huge data sets or advanced model. Because of this inefficiency, simple RNNs are inadequate for real world applications requiring great accuracy and speed. Here is the question 3.3 LSTM neural network and the limitations of simple RNNs. Long short term memory network or form of recurrent neural networks that addresses some of the fundamentals. One of the primary reasons why LSTM are effective in their usage of gates. These gates are tiny neural networks with each LSTM until they regulate the flow of data. The three essential gates input, forgot, and output work together to determine which information should be added to or removed from memory. The gating mechanism guarantees the critical information is preserved longer, which irrelevant information is removed as a result of LSTM outperform simple RNNs in terms of long-term efficiency, as the latter tend to forget previous inputs due to vanishing gradient problem. Lastly, LSTMs are better at learning from data that has a lot of different trends. They can escape being overhealed by noise in the data by choosing the forgot information that isn't important to them. In jobs where only certain parts of the sequence are important, LSTMs can focus on those parts and ignore the rest, which is not possible with the simple RNNs. Here is the references, and here LSTM with retail sales data. One is model design and training and result. In model design, two LSTM layers, 50 neuron each, 20% dropout, 30 time step sequences. In training, 80% training, 20% testing, 50 epochs, batch size of 32. Coming to the results, prediction failed to capture variabilities in sales data. Here is the part 4, LSTM with time series data. Here is the diagram. And in this report, there is LSTM with the time series data, collection of dataset and pre-processing. I used part 1 retail sales dataset which has more than 500 data points for time series analysis. The total amount property was chosen as the numerical variable to get the data ready for the LSTM model. It was grouped by data, adjusted to a range of 0 to 1 using minimum max scaling, and turned into 30 time step sequences. The sample was ready for training after these steps of processing. Design with core parameters. Percentage of data for testing 20%. LSTM layers is 2. Neurons in each LSTM layer is 50. Dropout layer is dropout rate 20%. Length of input sequence 30. Batch size of training is 32. Number of epochs is 50. Here is building, training, testing, evaluation of the data. Here are all the models of the design. Coming to buildings, the model structure was made up of two LSTM layers with each of 50 neurons and then output thick layer. To keep both LSTM layers from fitting too well, 20% failure rate was used. It has the structure of 31, which means it has 30 time steps as input and one future of total output. Training. The model was trained on 80% of dataset while the remaining 20% was allocated for validation. The training was performed by 50 epochs with the batch size of 32. The utilized loss function was mean square error and the Adam optimizer was implemented to optimize the weight. Testing. The model was accessed using the 20% dataset post training. The test loss was computed to evaluate the model generalization to fresh data. The prediction of training data were compared with the actual sales figures. Evaluation. The model's performance was shown by a graph comparing the actual sales figure with the projected sales figures. The graph illustrates the model prediction remained consistently stable as fixed values, whereas the actual values displayed considerable variability. This suggests the model failed to account for the significant variations in the sales data, leading to decreased accuracy. Retaining and forecasting process. Forecasting value is 1166.3009. In this model, the results to findings showed all through the model successfully converged during the training. The volatility seen in the actual sales number did not affect the model's predictions. This may be seen in the evaluation part, which when the actual data speaks and thoughts contrast with the projected line, which is comparatively flat. Although it gives an estimated for the next sales value, the prediction value of 1166.30 indicates that more model tuning is required to increase accuracy and better capture dynamic trends in the dataset. Coming to part 5, redesign the neural networks. In this redesign, increased testing data is 30% of dataset used for testing, enhanced model structure, 2 LSTM layers, 100 neural networks each, 50 time step sequences, extended training, 100 epochs with batch size of 32. Here is the diagram of redesign of neural networks. Input layer, RNN layer redesigned, output layer. Purpose of redesigned LSTM neural network is after analyzing the initial performance of the LSTM network, I proposed the following changes to improve model. Incorrect testing data percentage. Changed the testing data percentage from 20% to 30%. Better evaluate the model generalized performance. Increase the number of LSTM layers. Increase the number of LSTM layers from 1 to 2 layers. This improves the model ability to capture complex temporal patterns. Adjust the number of neurons. Dropout regularizations. Batch size and epochs. Set the batch size to 32 for stable parameter updates. Increase the number of epochs to 100 to allow more training iterations and better convergence. Core parameters is LSTM layers 2, neural neurons per layer is 100, input sequence length 50, batch size 32, epochs 100. Performance comparisons. Here is part 4 model and part 5 model. Part 4 model is struggled with retail data value variability higher than test loss. In Part 5 model, accurately captured sine wave patterns significantly reduced test loss. Here is the model structure, training and testing, retraining and forecasting. Here is the results and conclusion. Here is the graph shown in these results. The modified STL model did well. The comparison actual and expected sine waves values revealed a rather precise alignment, showing showcasing its enhanced capacity to learn the periodic structure of sine wave. Here is the graph training and validation loss curve. Coming to the part 6, compare neural network performance. Here is the key takeaways. Model 1, model data fit. Important of aligning models design with dataset complexity. Continuous improvement. Refinement through critical thinking enhances neural network performance. Here is the compare neural network performance. The ability of LSTM models from part 4 and 5 learn and generalize was evaluated to ascertain how the suggested modifications affects them. The two networks are thoroughly compared below depending on the design, training, and test results. Here is the graphs. Coming to part 7, project report. Part 1, time series dataset. Part 2, simple RNN with sine wave data. Here, all the steps we have done: data preparation, model composition, training results. In part 3, understanding gradient problems, the concept of vanishing and expanding gradient problems were employed to investigate the constraints of simple RNNs. The vanishing gradient problem is a challenge for simple RNNs to learn long-term dependencies because error signals diminish as they propagate backward. Here is the part 4, LSTM with time series data. The retail sales dataset was used to train an LSTM network for predicting sales totals. The total amount column was normalized and grouped into sequences of 30 time steps. Model design. Here is the model design. Layers to LSTM layers with 50 neurons each. Dropout is 20% to prevent overfitting. Training parameters 80% training and 20% testing. 50 epochs, batch size of 32. Here is the results. Coming to part 5, redesign of neural networks. In part 6, comparison of neural network performance. The impact of the redesign was accessed by comparing the part 4 and part 5 models. In part 4, the model encountered difficulty in adjusting to the variability of retail sales data, resulting in the predictions that were unreliable and failed to capture dynamic trends. The prediction was inaccurate and the test loss was higher. In the part in part 5, the redesigned model demonstrated exceptional performance on the similar sine wave data accurately despite peaks, valleys, and trends. The test loss was significantly reduced and the prediction closely matched the actual values. This comparison shows how important it is to make sure that the model design and parameters fit the information. To make them run faster, more advanced tuning and extra layers are needed for complex datasets like store sales. In the conclusions, this project explored the strengths and weaknesses of RNNs and LSTMs in time series forecasting. The initial model encountered difficulties when dealing with integrate data. However, the redesigned LSTM demonstrates the Substantial, substantial performance enhancement can be achieved by making deliberate adjustments. In this, the significance of confining the dataset, employing critical thinking, and refinancing model to achieve superior outcomes was underscored. In this project, showed the flexibility and effi- efficiency of neural networks for time series task. Thank you.